It's the most powerful technology of our time. But how does artificial intelligence actually work? We're pulling back the curtain. This is AI Deconstructed.
In our last episode, we deconstructed the engine of learning itself, gradient descent and backpropagation. We established that backpropagation is a remarkably clever algorithm, a way to compute the slope of the error with respect to every single weight in the entire network. It's the chain rule from calculus, applied recursively layer by layer, backwards from the final error. It tells each weight exactly how to nudge itself, either up or down, to collectively reduce the network's overall mistake. We now have an architecture, the multi-layer perceptron, and a powerful algorithm to train it. But a powerful engine is useless if the transmission is broken. What if the nudges we calculate at the end, at the output layer, are clear and strong, but by the time that signal travels backward to the first few layers, it has faded to an infinitesimal whisper? What if the gears of our network are designed in a way that they get stuck and refuse to pass the learning signal along? This is not a hypothetical. For decades, it was the single biggest barrier preventing us from building truly deep, powerful neural networks. In the intricate architecture of a neural network, we often focus on the grand structures, the layers, the connections, the sheer scale of modern models. But today, we're zooming in on the smallest, most fundamental point of action, the individual neuron. Imagine a biological neuron in your brain, receiving signals from thousands of others. It listens, it aggregates, and then it makes a decision: to fire or not to fire, to pass the message along or to remain silent. This singular moment, this spark of activity, is the basis of all thought and computation in the brain. In an artificial neural network, this critical decision is governed by a small, often overlooked mathematical function called the activation function. It's the gatekeeper at the exit of every neuron, determining what signal, if any, gets passed to the next layer. On the surface, it seems like a minor detail, but as we'll discover today, this function is the unsung hero of deep learning. It is the component that single-handedly transforms a simple, rigid chain of linear calculations into a dynamic, flexible network capable of learning the breathtakingly complex patterns of our world. From identifying a cat in a photograph to understanding the nuances of human speech. Our objectives today are to unravel their profound importance. We'll explore why they are not just an option, but an absolute necessity for deep learning. We'll journey through the history of the most common activation functions, from the early pioneers to the modern workhorses, and see how their evolution tells the story of deep learning itself. By the end, you'll understand that the choice of activation function isn't just a technical tweak. It's a fundamental decision that can make the difference between a network that learns and one that fails completely. Before we can appreciate the role of the activation function, we need to briefly revisit how a neural network learns. This process is a beautiful two-part dance between an optimization algorithm and a method for calculating direction. Think of it as a hiker trying to find the lowest point in a vast, foggy mountain range. The first part of the dance is gradient descent. This is our hiker. The goal is to minimize the network's error or loss, which is like finding the bottom of the deepest valley in the mountain range. The hiker starts at a random point and needs to take steps downhill. But in the fog, how does the hiker know which way is down? That's where the gradient comes in. The gradient is a vector that points in the direction of the steepest ascent. So, to go downhill, our hiker simply takes a step in the opposite direction, the negative gradient. This process is repeated, step by step, until the hiker reaches the bottom of the valley, where the network's error is at its minimum. But this raises a critical question. How does the network calculate this gradient for every single one of its millions of parameters, or weights? This is where the second part of the dance comes in: backpropagation. Backpropagation is the hiker's sophisticated navigation system. After the network makes a prediction and calculates its error at the output, backpropagation takes that error signal and propagates it backward, layer by layer, from the output all the way to the input. Using a clever application of the chain rule from calculus, it efficiently calculates the exact contribution of each weight to the final error. In other words, it computes the gradient of the loss function with respect to every weight. Here is the crucial connection. Gradient descent, our hiker, is completely reliant on the directions provided by backpropagation, the navigation system. The entire learning process hinges on the quality of this gradient signal. The chain rule used in backpropagation involves multiplying the derivatives of all the functions that the data pass through on its forward journey. This includes the derivative of the activation function at each and every layer. This means the mathematical properties of the activation function are not isolated. They are a recurring critical link in the backpropagation chain. If that link is weak, if the derivative of our activation function is problematic, it can poison the entire process. The gradient signal can weaken, vanish, and our hiker, gradient descent, becomes lost in the fog, unable to take another step. The network stops learning. This fragile, symbiotic relationship is why a deep dive into activation functions is not just an academic exercise. It's essential for understanding why deep networks work at all. So, if the derivative of the activation function can cause so much trouble, why bother with one at all? Why not just let the weighted sum of inputs pass directly to the next layer? The answer to this question lies at the very heart of what makes deep learning powerful, and it exposes the profound limitations of a purely linear system. Inside a single layer of a neural network, before the activation function, the computation is fundamentally linear. As we've discussed, it's a weighted sum, a matrix multiplication of the inputs with the layer's weights, followed by the addition of a bias term. Now, imagine we build a deep network by stacking several of these linear layers on top of each other, but with no activation functions in between. What have we accomplished? Mathematically, almost nothing. A linear transformation of a linear transformation is still just a linear transformation. Let's use a simple analogy. I'll call it the linear sandwich. Imagine the first layer's function is y equals 2x plus 1. That's a linear function. Now we feed its output, y, into a second layer which performs the function z equals 3y minus 2. This is also a linear function. What is the final function that maps our original input x to our final output z? We can just substitute the first equation into the second. We get z equals 3 times the quantity 2x plus 1 minus 2. We distribute the 3, which gives us z equals 6x plus 3 minus 2. And we simplify. Z equals 6x plus 1. What is z equals 6x plus 1? It is just another linear function. We stacked two linear layers, and all we got was a single, different linear layer. The same holds true for the matrix operations in a real network. Let's say your input is x. The first layer computes z sub 1 equals w sub 1 times x plus b sub 1. The second layer takes that output and computes z sub 2 equals w sub 2 times z sub 1 plus b sub 2. If we substitute the first equation into the second, we get z sub 2 equals w sub 2 times the quantity w sub 1 times x plus b sub 1, all plus b sub 2. Expanding this gives us z sub 2 equals the quantity w sub 2 times w sub 1 times x, plus the quantity w sub 2 times b sub 1 plus b sub 2. If we define a new weight matrix W prime equals W sub 2 times W sub 1, and a new bias vector B prime equals W sub 2 times B sub 1 plus B sub 2, the entire two-layer system simplifies to Z sub 2 equals W prime times X plus B prime. This is the exact mathematical form of a single linear layer. This means that no matter how many linear layers you stack, 10, 100, 1,000, the entire network can be mathematically collapsed into a single linear layer. A deep linear network has no more expressive power than a shallow one. It's fundamentally incapable of learning anything more complex than a simple linear relationship, like the kind you'd find in basic linear regression. To make this intuitive, imagine your data points are arranged in two intertwined spirals, one for each class. Your task is to draw a boundary to separate them. A linear model can only draw a straight line. No matter what you do, a single straight line can never separate those spirals. Stacking more linear layers is like being given more rulers, but with the constraint that you can only lay them end-to-end in a perfectly straight line. You haven't gained any new capability. You're still stuck with the problem of the straight line. This is where the activation function makes its grand entrance. By applying a nonlinear transformation to the output of each layer, it fundamentally breaks the chain of linearity. The output of one layer is no longer a simple linear function of the previous one. This single step is what gives a deep network its power. Think of it this way. The linear weighted sum allows the network to stretch and rotate the data. The nonlinear activation function allows it to bend and fold the data. By stacking these operations, stretch, rotate, bend, over many layers, the network can perform an incredibly complex origami, folding the data landscape until the different classes are neatly separated. Without the bend step, all it can do is stretch a line into a longer line. Each layer can now learn a new, more complex representation of the data it receives from the layer before it. The first layer might learn to draw simple linear boundaries, but by passing those results through a nonlinear activation function, the second layer is no longer just combining straight lines. It can learn to bend and warp those lines. The third layer can take those bent lines and combine them into even more complex curves and shapes. This layer-by-layer increase in complexity is what allows a deep neural network to eventually learn the intricate, nonlinear decision boundary required to separate our intertwined spirals. This capability is formalized in a cornerstone of neural network theory, the universal approximation theorem. It states that a neural network with just one hidden layer containing a finite number of neurons and a nonlinear activation function can, in theory, approximate any continuous function to any desired degree of accuracy. The nonlinearity is the key that unlocks this incredible power. It's the phase transition that elevates the model from a simple statistical tool to a universal function approximator. The historical importance of this cannot be overstated. In the early days of AI research, simple models like the perceptron, which lacked nonlinear activation functions, famously failed to solve even basic nonlinear problems, like the XOR logic problem we discussed back in episode 12. This failure was so significant that it contributed to a massive loss of confidence and funding in the field, leading to what became known as the first AI winter. The nonlinear activation function wasn't just a missing component. Its absence was a roadblock that stalled the progress of an entire field for years. It is the spark that was needed to reignite the quest for artificial intelligence. Now that we understand why we need nonlinearity, let's explore the functions that provide it. We'll start with one of the earliest and most historically important players, the sigmoid function, also known as the logistic function. The sigmoid function has a simple and elegant mathematical form. F of x equals 1 divided by the quantity 1 plus e to the power of negative x. When you plot it, you get a characteristic S-shaped curve. Let's verbally parse that because it's not as scary as it looks. The x is our weighted sum. What happens when x gets very, very large and positive? E to the power of a large negative number, that's e to the negative x, gets incredibly tiny, approaching 0. So the formula becomes 1 divided by 1 plus 0, which equals 1. So, for large positive inputs, sigmoid outputs 1. What happens when x gets very, very large and negative? E to the power of a large positive number, that's e to the negative x, becomes enormous. The formula becomes 1 divided by 1 plus a huge number, which approaches 0. So, for large negative inputs, sigmoid outputs 0. And what happens when x is exactly 0? E to the power of 0 is 1. The formula is 1 divided by 1 plus 1, which is 0.5. Its most important property is its output range. No matter what real number you feed into it, whether it's negative 1 million or positive 1 million, the sigmoid function will squash that value into a range strictly between 0 and 1. This property makes it incredibly useful for a specific task, binary classification. Because its output is always between 0 and 1, it can be naturally interpreted as a probability. For this reason, the sigmoid function became the go-to choice for the final output layer of a network designed to answer a yes or no question. Let's consider a real-world example, a medical diagnosis model designed to predict the probability that a patient has heart disease based on clinical data like age, blood pressure, and cholesterol levels. The network processes these inputs through its hidden layers and produces a final number. If we apply the sigmoid function to that final number, the output might be 0.87. We can interpret this as the model predicting an 87% probability that the patient has heart disease. This probabilistic output is far more useful to a doctor than a simple yes or no, as it conveys the model's confidence in its prediction. This application in binary classification, from medical diagnosis to spam detection, is where the sigmoid function truly shines. For a time, the sigmoid function was used not only in the output layer, but also in the hidden layers of networks. However, as researchers tried to build deeper and more powerful models, they ran into a catastrophic problem, a problem for which the sigmoid function was a primary culprit. This is the infamous vanishing gradient problem. To understand it, we have to look at the derivative, or the slope, of the sigmoid curve. The function is steepest near the center, for inputs around 0. But as the input becomes very large, either positive or negative, the curve flattens out and becomes nearly horizontal. When a function is flat, its derivative is close to 0. In fact, the maximum value of the sigmoid's derivative is only 0.25, and for most inputs it's much, much smaller. Now remember our discussion of backpropagation. To update the weights, we multiply gradients together as we move backward through the layers. Each time we pass through a sigmoid activation, we multiply by its derivative. So we are repeatedly multiplying by a number that is, at best, 0.25 and usually much smaller. This has an exponential effect. The gradient signal, which starts at the output layer, shrinks dramatically with every layer it passes through on its way back to the input. Let's use an analogy. Imagine you're at one end of a very long hall and you need to get a message to someone at the other end. But you can't shout. You can only whisper it to the person next to you, who then whispers it to the next person, and so on. With each whisper, the message gets a little fainter. By the time it reaches the end of the hall, it's either completely distorted or has faded into silence. This is exactly what happens to the error signal in a deep network with sigmoid activations. We are multiplying a chain of small numbers. Error times 0.2 times 0.1 times 0.05 times 0.15, and so on. The gradient vanishes. The consequence is devastating. The early layers of the network, the ones at the beginning of the hall, receive a gradient signal that is so small it's effectively zero. Their weights barely get updated, if at all. They stop learning. Since these early layers are responsible for detecting the most fundamental, low-level features in the data, like edges and corners in an image, their failure to learn cripples the entire network's ability to perform its task. The vanishing gradient problem was a primary barrier that for years prevented researchers from successfully training truly deep neural networks. The issues with the sigmoid function, particularly the vanishing gradient, spurred researchers to look for alternatives. One of the first and most logical improvements was the hyperbolic tangent function, or tanh for short. Mathematically, tanh is defined as f of x equals the quantity e to the x minus e to the negative x, all divided by the quantity e to the x plus e to the negative x. If you plot it, you'll see it looks very similar to the sigmoid function. It has the same characteristic S-shape. However, there is one crucial difference: its output range. Instead of squashing values between 0 and 1, tanh squashes them between -1 and 1. This might seem like a small change, but it has a significant practical advantage. The output of the tanh function is zero-centered. Why does this matter? Consider the activations coming out of a hidden layer using sigmoid. They are always positive, ranging from 0 to 1. When these positive values are fed into the next layer, it can be shown that the gradients used to update that next layer's weights will all have the same sign. They will either all be positive or all be negative. This restricts the way the weights can be updated, forcing the learning algorithm to take a suboptimal, zigzagging path towards the minimum error, which can slow down convergence. It's like trying to drive a car that can only make left-hand turns. You can still get to your destination, but it's going to be a very inefficient and awkward drive. Because tanh's output is centered around 0, producing a mix of positive and negative values, it breaks this pattern. The gradients are more varied, allowing for a more direct and efficient path for gradient descent. In practice, this often leads to faster training compared to sigmoid. For this reason, tanh became the preferred choice over sigmoid for hidden layers in many networks. This progression from sigmoid to tanh is a perfect example of the iterative, problem-solving nature of machine learning research. tanh didn't solve the core, show-stopping issue of vanishing gradients. Like sigmoid, its curve also flattens out for large inputs, causing its derivative to approach 0. However, it did address the secondary problem of non-zero-centered outputs, providing a tangible, incremental improvement in performance. It was a step in the right direction, but the hunt for a true solution to the vanishing gradient problem was still on. The solution, when it arrived, was a radical departure from the smooth, elegant curves of sigmoid and tanh. It was something far simpler, almost brutishly so. Meet the rectified linear unit, or ReLU, the modern default activation function for nearly all deep learning applications. The mathematical formula for ReLU is deceptively simple. F of x equals the maximum of 0 and x. That's it. If the input to the function is positive, it passes through completely unchanged. If the input is negative, it is simply clipped to 0. This simplicity is ReLU's superpower. Its first major advantage is computational efficiency. Unlike sigmoid and tanh, which require calculating expensive exponential operations, ReLU is just a simple comparison and thresholding operation. For a network with millions of neurons being updated thousands of times, this difference in computational cost is enormous and leads to significantly faster training times. Secondly, ReLU introduces sparsity into the network. Because any negative input is mapped to zero, it's likely that for any given input sample, a significant fraction of the neurons in the network will be inactive, or off. This sparse activation is not only more computationally efficient, but is also thought to help the network learn more robust features and can reduce the risk of overfitting. But this raises a common point of confusion. If ReLU is just two straight lines, a flat line at 0 and a diagonal line with a slope of 1, how can it possibly be a nonlinear function? It is what's known as a piecewise linear function. While each piece is linear, the function as a whole is nonlinear because of the sharp kink or corner at 0. A single ReLU neuron by itself isn't very expressive. But the magic happens when you combine thousands or millions of them in a network. Each neuron learns its own weights and bias, which effectively shifts where this kink occurs. By adding together all these simple kinked functions, the network can collectively approximate any arbitrarily complex, smooth, nonlinear function. It's like building a beautiful, smooth sculpture out of countless tiny, straight Lego bricks. The primary reason for ReLU's dominance, however, is its elegant solution to the vanishing gradient problem. Recall that with Sigmoid and Tanh, the gradient signal shrinks because the derivative of the function is always less than 1 and often close to 0. Now, consider the derivative of ReLU. For any negative input, the function is flat, so the derivative is 0. But for any positive input, the function is y equals x, a line with a slope of 1. Therefore, its derivative is a constant one. This is the breakthrough. During backpropagation, for any neuron that was activated, meaning it had a positive input, the gradient signal passes through it completely unchanged. It is multiplied by 1, so it doesn't shrink at all. Let's rerun our whisper down the lane analogy. Now, every person in the line who is active shouts the message at full volume to the person behind them. Error times 1 times 1 times 1 times 1, and so on. The error signal can propagate backward through even very deep networks without vanishing, ensuring that all layers, even the earliest ones, receive a strong learning signal. This property was one of the key innovations that finally unlocked the ability to effectively train the very deep neural networks that power the modern deep learning revolution. The story of ReLU is a powerful lesson in pragmatic engineering over theoretical purity. Sigmoid and Tanh are mathematically cleaner. They are smooth and differentiable everywhere. ReLU is messy. It's not differentiable at 0 and has this abrupt change in behavior, yet its practical properties, its computational speed, and most importantly, its solution to the vanishing gradient problem, made it vastly more effective for building the deep networks that researchers had long dreamed of. Here we must also address a common misconception. Many people look at the S shape of sigmoid and think it's more biological or natural. The brain's neurons do saturate, after all. They have a maximum firing rate. But here we have a crucial lesson. What is biologically plausible is not always what is mathematically effective for an optimization algorithm like gradient descent. Our goal isn't to build a perfect, wet brain. Our goal is to build a system that can learn from data using gradients. ReLU's gradient properties are simply vastly superior for that task. The simpler, less biological function turned out to be the more powerful one. But no solution is perfect. For all its advantages, ReLU has a significant and potentially fatal flaw: the dying ReLU problem. Here's how it happens. A neuron's input is the weighted sum of the outputs from the previous layer, plus a bias term. During training, these weights and biases are constantly being updated. It's possible for a large gradient to flow through a ReLU neuron, causing a large update to its weights and bias. This update might be so large that it pushes the neuron into a state where its input will be negative for any data point that it ever sees in the training set. If the neuron's input is always negative, its output, thanks to ReLU, will always be 0. Now think about backpropagation. The derivative of ReLU for negative inputs is also 0. This means that once a neuron gets into this state, the gradient that flows through it will forever be 0. Its weights will never be updated again. The neuron becomes stuck, inactive, and effectively dies. It becomes useless, a piece of dead computational wood in the network. It contributes nothing to the network's learning process from that point forward. In a worst-case scenario, a large portion of the neurons in a network can die, drastically reducing the model's capacity and potentially halting learning altogether. What causes this? The two most common culprits are a learning rate that is set too high, which allows for these massive, destabilizing weight updates, or initializing the network with a large negative bias, which can push neurons into the inactive state from the very beginning. This problem showed that while ReLU had solved the vanishing gradient, it had introduced a new, more subtle challenge that needed to be addressed. The response from the research community to the dying ReLU problem was not to abandon ReLU, but to refine it. This led to the creation of a whole family of related activation functions, each designed as an elegant, targeted solution. The first and most famous variant is leaky ReLU. The idea is simple. Instead of the function being 0 for negative inputs, we allow a small, non-zero constant slope. For example, the function might be defined as f of x equals x for positive inputs, but f of x equals 0.01 times x for negative inputs. This tiny leak ensures that there is always a small, non-zero gradient, even when the neuron is inactive. This gives a dead neuron a chance to be revived, as its weights can still be updated, albeit slowly. Taking this a step further, researchers developed parametric ReLU, or PRELU. In PRELU, the slope for the negative inputs is not a fixed hyperparameter like 0.01. Instead, it's a learnable parameter. The network itself gets to decide the optimal slope for each neuron during the training process, adapting it to the specific data and task. Another popular variant is the exponential linear unit, or ELU. For negative inputs, ELU uses a smooth, curved exponential function that eventually saturates at -1. This has two potential benefits. First, like leaky ReLU, it has a non-zero gradient for negative inputs, preventing neuron death. Second, because it can output negative values, it can help push the average activation of a layer closer to 0, giving it some of the zero-centered benefits of the tanh function, which can speed up learning. This evolution from ReLU to its variants is a perfect example of the mature iterative engineering that drives modern AI. A major problem, vanishing gradients, was solved with a pragmatic, if imperfect, solution, ReLU. A new, smaller problem emerged: dying neurons, which was then patched with a series of targeted, intelligent modifications like leaky ReLU, PRELU, and ELU that preserved the core benefits of the original solution. We've covered a lot of ground, exploring the mechanics, pros and cons of the three major families of activation functions. To bring it all together, let's lay out a direct comparison to serve as a practical guide for anyone building a neural network. Let's walk through it, feature by feature, for our three main contenders, Sigmoid, Tanh, and ReLU. First, the mathematical formula. For sigmoid, it's sigma of x equals 1 divided by the quantity 1 plus e to the negative x. For tan h, it's tan h of x equals the quantity e to the x minus e to the negative x, all divided by the quantity e to the x plus e to the negative x. And for ReLU, it's the simple ReLU of x equals the maximum of 0 and x. Next, the output range. Sigmoid gives you values between 0 and 1, tan h gives you values between -1 and 1, and ReLU gives you values from 0 to infinity. Is the function zero-centered? For sigmoid, no, its output is always positive. For tan h, yes, which is a key advantage. For ReLU, no, its output is also always non-negative, which is one of its downsides. Does it suffer from the vanishing gradient problem? For both sigmoid and tan h, the answer is a definitive yes. Their saturating, S-shaped nature makes them unsuitable for very deep networks. For ReLU, the answer is no, at least for positive inputs, which is its main claim to fame. Does it have a neuron death issue? For sigmoid and tan h, not in the same way. Their gradients get small, but they never become exactly zero for a whole region of the input space. For ReLU, yes, this is its primary weakness. What about computational cost? Sigmoid and tan h are moderately expensive due to their exponential terms. ReLU is extremely cheap, involving only a simple comparison. Finally, what are the common use cases? For sigmoid, it's almost exclusively used in the output layer for binary classification problems. For tan h, it's sometimes used in the hidden layers of shallower networks, or in certain recurrent neural network architectures. And for ReLU, it is the undisputed default choice for the hidden layers in almost all modern deep networks, especially in convolutional and standard feed-forward networks. This comparison makes the modern consensus clear. Start with ReLU or one of its variants for your hidden layers. Only deviate if you have a specific, well-understood reason to do so. Let's ground this comparison in some tangible, real-world applications to see how these choices play out in practice. The classic use case for the sigmoid function remains in binary classification tasks, where a clear probabilistic output is needed. We've already mentioned medical diagnosis, where models predict the likelihood of conditions like heart disease or cancer based on patient data. This extends to many other fields: finance, for predicting whether a customer will default on a loan; marketing, for predicting whether a user will click on an ad; and email systems, for classifying a message as spam or not spam. In all these cases, the network's hidden layers might use a more modern activation function, but the final output neuron will almost certainly use a sigmoid to produce that crucial probability score between 0 and 1. Meanwhile, ReLU and its variants are the engine room of modern deep learning, especially in the field of computer vision. Its ability to train deep networks efficiently has made it the standard choice for the hidden layers of convolutional neural networks, or CNNs. Landmark models that revolutionized image recognition, like AlexNet, VGGNet, and ResNet, all rely heavily on ReLU. These are the types of models that power the technology around us every day. The object detection systems in self-driving cars that identify pedestrians and traffic signs, the medical imaging systems that help radiologists detect tumors in X-rays and MRIs, and the facial recognition systems used in security and social media photo tagging. In these incredibly deep and complex architectures, the non-saturating, computationally cheap nature of ReLU is not just an advantage, it's an enabling technology. This reveals a clear and sophisticated design principle in modern neural network architecture. The choice of activation function is not uniform across the network. Instead, it's context-dependent. For the hidden layers, whose job is to build increasingly complex representations of the data, you use the function that best facilitates deep, efficient learning, which is almost always ReLU or a member of its family. For the output layer, whose job is to format the network's final answer into a useful form for the specific problem, you use a specialized function, Sigmoid for binary classification, a function called softmax for multi-class problems, or even a simple linear function for regression tasks where you want to predict a continuous value. This hybrid approach combines the strengths of different functions to build the most effective model possible. Today, we've journeyed deep into the heart of the artificial neuron to uncover the power of the activation function. We started by understanding that for a neural network to learn anything beyond a simple straight line, it needs a spark of non-linearity. We saw how early attempts with functions like Sigmoid and Tanh were a crucial first step, but were ultimately crippled by the vanishing gradient problem, which halted the progress of deep learning for years. Then came the revolution in simplicity, ReLU, a function so straightforward it seems almost naive, yet its properties solved the vanishing gradient problem, enabled the training of truly deep networks, and became the modern standard. But we also saw its own flaw, the dying ReLU problem, and the elegant family of variants like leaky ReLU that were engineered to fix it. The key takeaway is this: activation functions are the small but mighty components that unlock the immense power of deep neural networks. They are a perfect case study in the evolution of AI research, a story of identifying fundamental barriers, engineering pragmatic solutions, and iteratively refining those solutions in a relentless pursuit of more capable and intelligent models. The concepts we've discussed today are not just theoretical, they are the essential building blocks for the more advanced architectures we'll be exploring in this series, and that brings us to our next episode. Now that we have the spark of nonlinearity, we're ready to build a network that can truly see. Next time, we'll be diving into convolutional neural networks, or CNNs, the specialized architecture that completely transformed the field of computer vision. We'll explore their core components, which are inspired by the human visual cortex. We'll look at convolutional layers, where small filters, also called kernels, slide across an image to detect basic features like edges, corners, colors, and textures. Then we'll examine pooling layers, which cleverly downsample these feature maps to make the representations more robust and computationally manageable. And here is the direct link to today's topic. After every single one of those convolutional operations, the network applies a nonlinear activation function. And which one do you think it is? That's right, ReLU. It is the ReLU activation that takes the simple features detected by the filters and allows the network to combine them in complex nonlinear ways, building up a hierarchical understanding of the image. It's how a CNN goes from seeing simple edges in the first layer to recognizing shapes like eyes and noses in the middle layers, to finally identifying a complete face in the output. The knowledge you've gained today about activation functions is the direct prerequisite for understanding how the magic of modern computer vision happens. Join us next time as we build on that foundation and explore the incredible world of convolutional neural networks.
You've been listening to AI Deconstructed. Join us next time as we unpack another layer of the technology shaping our future. Until then, stay curious. Subscribe for more.